So this is our ME106 project. I'm Kyle.
Tim.
Jordan.
And this is the oxygen hose minding system. So this is our ME106 group. We're the oxygen hose minding system group that Dr. Furman prompted us to work on. So here's our project. We use two drums that are set up almost touching one another to pull through this like 5/16 inch oxygen hose that's pretty standard that Jordan got from an actual hospital. So this is the actual material that we would be using if this were a final product. The two drums are connected to each other. Well, actually, I'm sorry. The two drums are connected to an acrylic frame that we cut in the ME106 lab on the Epilogue printer, the laser cutter there. It's made out of 1/4-inch acrylic. Attached to that, we have 4 flange-bearing mounts that we milled to accommodate 8 skateboard bearings. On this side, we have 2 pulleys with a belt set up in a V so that when one drum spins in one direction, the other spins in the opposite direction. On the opposite side, we have a gear to another gear on a DC motor that is used to power the whole system through operation of a remote. Yeah, we tried to make it as sturdy as possible because we weren't sure how it was going to react under the forces of the motor, so that's why there's this big old bar here and why there's so many brackets attached to both of the board here as well as different acrylic pieces. On the front we have a acrylic mounting plate for a guide that manages the hose through the rollers, and then on the reverse side there's another piece of 3/8 PVC that is also used on the opposite side. That piece is actually connected to a servo to sweep the hose in a coil. So that's pretty much like structural. And so now Tim will talk about the electrical.
For our electrical configuration, we lay our setup out similar to what the printer carriage. It was so red.
We can try again. Yeah, because we didn't introduce ourselves either. I totally skipped that.
But then yours was really good already. So.
Can do it again.
We can.
No. We can keep your part, and then I can just.
It's really blanked half like mid-talk. I was like, bleh.
Oh.
I
can still edit it in.
If you want, and because you know what I was thinking.
Everything else was really.
No, ma'am.
Okay. So this is it. This is the controller. There's a safety button, and then the forward and backwards buttons. And see, if you press those buttons without pressing the safety button, it doesn't go. So that's one of our safety devices. So if you press the safety button and then the forward button, it starts rotating forward and letting it out. And then if you let it go, see, it stops. So then if you go press the backwards button, then it goes the other way and starts reeling it back in. And if you come and look in the back, when it's going, there's a servo in the back controlling its outlet. The point of that was to try to get it to spool. In the back, and that sort of worked. It kind of ended up in a figure-8 pattern, but it's better than nothing, and that's something we would have changed if we had more time. And then, let's see, we also have a hall sensor. I think I'm going the wrong way. To where if it pulls in too much, it should stop, because it'll trip the hall sensor, which is right here. Oh, see, stops, and then it won't keep going.
Go.
All right, my name is Tin, and I'll be covering the electrical configuration for this project. So for this particular project, we had our layout similar to the printer carriage lab that we did in the ME106 lab. And basically the components that we're using is a Arduino microcontroller, a motor driver board. We're powering the Arduino with a 9-volt battery, and we have a breadboard that is connecting all the connections for that. And we also have a Hall sensor up here, and what the Hall sensor is actually doing is basically it's acting like a limit switch, so that once the magnet reach the Hall sensor, it's going to stop it's going to cut power to the motor so that it doesn't reel all the oxygen hose inside and possibly injuring the user. And also, what we have back here is a DC motor, and this particular DC motor is configured for a 12-volt battery. We have a servo back here that is the purpose that it's serving is basically it's going to sweep back and forth, organizing the oxygen hose so that it doesn't get tangled together. And we also have a power supply back here that is actually powering the motor, because the Arduino microcontroller is not sufficient. The power that the Arduino microcontroller is putting out is not sufficient to power the motor.
Alright, so in working on this project, learned a few things. Like Jordan, we learned that, or I learned that, yeah, it matters what lead you plug in where. As far as the power source, we have a 12-volt power source, and there were 2 wires. We figured that if we were plugged the one lead into the motor board and the other into the ground, that it would, in fact, supply 12 volts, but in the opposite direction, which it does, but it ended up driving the current into an Arduino, actually 2 Arduinos that both fried in the process. I also learned that it's good to start on these kind of projects early, and to just kind of get your ideas down kind of at the beginning, so you don't have to change your design as you go through. To just, if you really think it through and engineer it well at the beginning, then it makes things a lot easier as you go along. Another cool thing that I learned was how to use a laser cutter, which I'd never done before, which is what we used to cut the frame, which I actually got my certification, so I'll be using it in the future too. So that was a really cool thing that I got out of this whole project. And yeah, I mean, just overall, learned a lot about circuitry, kind of a lot about structural design, which I know isn't part of the class, but still kind of important to engineering. And yeah, that's pretty much it. So it's a good project.
Did you just press OK or off?
I just press the thing again.
So I would say that the biggest thing that I learned was that it does matter which lead from the power supply you plug in where. Because I guess I misunderstood the lab instructor when he was saying to test the voltage of things. He said it didn't matter which lead you tested with the plus end, because it would just come up as negative on the screen, and I took that as meaning doesn't matter which end you plug in where, which didn't turn out to be the case. And we fried 2 Arduino boards by plugging the 12-volt lead into the ground line. And so we definitely learned that the hard way. So when we finally tested it with a multimeter and figured out that, yes, we were plugging it 12 volts into what was supposed to be ground, we fixed that and did not fry another one, and I know that I will not do that again.
So when I was working on this project, I found out that there is actually multiple types of Hall sensor. One of the Hall sensor worked in a way where if you had the magnet close to it, it'll take the state of the pin that it's reading from a low state to a high state, and when you bring the magnet away, take the magnet away, it'll bring it back to its low state. And another Hall sensor works in a way where if you bring the magnet in, it'll put it to a high state, but the only way you can put it back into a low state is switch the polarity of the magnet, and it will bring it back to a low state. So I had to figure out which one works best for this configuration, and it would be the first choice. It would be the first one that I just mentioned. And also, working on this project, I think that when we were testing out our design, the best way to do it was to test it in a modular way where we test each thing separately, such as running the motor separately from the servo and testing the Hall sensor separately, and then later incorporating all that together as one piece. So that's what I learned about this project.